Is that okay? All right, I don't hear anybody online. Is the sound okay? Yeah.
Can you share today lecture PPT so that I can share to all students?
I send it to Bharat. I had it on my draft since last night, and when I closed my computer today, I found it, so I sent it late. Sorry about that. Alrighty, I guess I don't have to speak too loud today because I can hear myself, so that's great. Good morning, everyone. Okay, so we're gonna go into the last day of the course today. Well, we're gonna talk a little bit about stabilization. Soil stabilization has to deal with all these problematic soils that we saw with low volume roads and also to pave roads. And obviously, with the time we have today, only 2 hours, we're going to go into very general considerations of mechanical and chemical stabilization. So what you're going to be learning today is about chemical and mechanical stabilization, and I'm going to round it up on the second hour into the use of geosynthetics in roadway systems. Okay. So why subgrade improvement? Well, it is, I put in here extremely important if you want to ensure that it's going to be a long-lasting pavement structure without excessive maintenance and movement, right? Usually we avoid soils that are problematic. We just excavate, right? We just get rid of the soil as much as we can and as economically feasible as it is, right? As we can be. But when excavation is a problem, then the soil is not economically feasible to do that, and you need to stabilize that soil, right? So the objectives of stabilization can be probably summarized in few areas. One of the strength, the strengthening of the so everything has to do with the strength on that. Another one is the soil workability. Sometimes not even the stabilization has any value into the design of the road, but you need to do that in order to even start working on that, just to get the loaders and to get the equipment to start working on compacting the soils. Weather resistant work platform, and this one also goes into the workability at the beginning during the construction stage of your road. Swelling, now volume change, reduce swelling on expansive soils that you've seen the problem around, and mitigate also problems when we do have frost heave. The objectives, like I said, let's put them into stages in the construction. The first one will be the construction platform, right? When you have two dry, very, very wet soils, okay, and need to facilitate the compaction of that, this is when we use some stabilization as well, okay? In this case, the stabilization is usually not considered as a structural layer, okay? So even if the soil was very nice, stabilized, and you have a chemical stabilizing here, a platform, and you ended up with that platform under your pavement, it's usually not considered, okay, as a pavement layer, even if you gain some strength in there. The second will be the strengthen a weak soil and restrict the volume change of highly plastic materials, right? In this case, the modified material is usually given some structural value into the design procedures. Right? And the third one would be to reduce the moisture susceptibility, right? So that's what we do with expansive soils and frost susceptible soils. Ways to stabilize the soil, okay? Those are some of them are mechanical. You do something mechanically to do the stabilization. You put more gravel. Mostly, this is the solution number one, right? The best solution is just get gravel and just use them, right? Get granular material to be larger or thicker. Or you blend it. You blend the material that you have, which is pretty weak, with material that is a little bit more, has more competency. Geosynthetics, this is a mechanical way to stabilize it. And the lightweight fields or surcharge, which you probably know in length for compressibility soils, right? We're not going to go to that in here. That's another whole course that I'm going to be teaching. Actually, we started teaching that yesterday, and I canceled my class in Arizona. But it's all about, compressibility and stabilizing the soils. But I think you are familiar with that on your compressibility class. And mixtures, you put a stuff on the soil. So you can put Portland cement, you can put lime, a combination of lime, fly ash. There are many things coming out right now that you can just mix the soil with and just try to create some chemical reactions to stabilize the soil. Asphalt or bituminous material also is used, pozzolanics and slags that are available commercially, and chemicals also to be added. And waterproofers like asphalt and geomembranes are also part of this stabilization method that we're going to see. Let's talk a little bit about the mechanical stabilization methods for pavement, and I brought at the end, you have always the reference that I use for this. There is a very nice reference that is available. It's by Ray Rollins and Rollins, 1996, and they do a very good job on summarizing on a big report the methods for low volume roads. And this one includes, again, like I said, more gravel, blending, geosynthetics, lightweight. They do have tables in here and what kind of soil type you can use this, right? Which one is more suitable, how these improve the soil, and some other considerations that you need to think when you need to decide, right? So you got the problem in there, you need to figure out what soil it is, okay? And if you go over there and check those tables, figure out what are the suitable, methods that you're going to have available for that, and what it's going to do to your soil. For example, blending. Blending is good for soil that are moderately clay material or plasticity, right? So when you do blending, what does that do to the soil? So improve degradation, reduce plasticity, reduce the breakage, and so forth, okay? If you want to add more gravel, that's not very good for clays, right? You can mix it very well. You just can't mix it, right? So the silts and clays, there are no benefits to that, right? You can just use it for other type of soils. And so let's go for some of those guys. So more gravel, right? So stabilization number one is you're going to have thicker granular layers. Okay, this is again, I will provide a working platform, which is pretty good. Do not provide a strengthening of the soil, of the subgrade, and it's going to be most often produce disturbance of the subgrade than that benefit. But now you can work on this guy. Used to reduce frost problems, and I'm going to check. Here is an example. Like for example, a common practice in the Northwest states in the United States. And actually, they use 1 meter of gravel to reduce the heat, for example. So I said, we don't want to get the frost, so they figured out what is the frost depth, okay? And they just put this in material that is not prone to swelling or just, having problems. So that's what they do. They can do, like for example, Washington State, that's very common to put 18 inches, okay? 18 inches of cap rock, that is called cap rock, beneath the pavement section to mitigate the frost action problems that they have. So this is the way they do it. They do the subgrade, they do the capping here, okay? They do subbase, the granular base, and the pavements, and then you can put any other stuff in there that you need to put, all right? But this is basically the capping layer goes below the subbase material, okay? Geotextiles and geogrids, we're gonna talk a little bit more in length in the second hour. It's used in combination with quality aggregate. We call it aggregate to adopt. And what it does is allows the access to the construction equipment. You put a geotextile, you put a geogrid, and now you can at least have a platform that will distribute the strength, a little bit better so you don't have punching failures when you just get your road equipment in there, and you got more general failure, okay? You can have failure, but it's general. Reduce the extent of stress on the subgrade, and one of the most important things that is being used lately is in the separation, provide separation. When you do have aggregates penetrating the subgrade, right? You don't know what the thickness is going to be anymore. You're going to have all this blended material in there. And the other one is the subgrade material has a lot of fines, okay? And if you get these subgrade fines invading your granular-based material, you're going to be creating a problem with the drainage, right? And these fines have a lot of suction. They will accumulate water in there, and you're going to have water right below the asphalt pavements of, or any sealing surface that you're going to have if you have an unpaved road, all right? So separation actually is a very important function of the geotextiles and the use. The primary long-term benefit is preventing, again, aggregate subgrade mixing and maintaining, therefore, the thickness of the base and subbase cleaner. Within the admixtures for the soil stabilization, again, Rollins has a very nice table in there in which they use they explain the benefits of Portland cement, lime fly ash, and so forth. So let's go a little bit on some of these guys. What the mixtures do is they do fill or partially fill the voids between the soil particles. Okay, this is what it is. And obviously we're going to talk a little bit about the chemical reactions that occur for some of them in here. But basically what it does is reduce the soil permeability. So obviously, increase the tortuosity of the flow through this particular material, which is good for us because what we don't want is water on the subgrade material, right? So if you stabilize some of these, then you're going to have less permeability and therefore less water on the subgrade material. That is your problem. So create a waterproof surface to protect the underlying layers on that, right? So this is important for that. There also, a problem that is that increase the density, okay? Increase the density of the material, right? And now for shearing behavior, instead of now getting into the contractive because you have a looser material, now you get into a more dilative, right? More dilative behavior for that. So there's going to be some change in the volume change behavior of the soil. And add cohesive strength. Now we can talk about cohesion, right? The cohesion strength. In reality, it does bond the particles together, right? Bonds the particles together. And it could be on a chemical reaction, physical reaction like flocculation, or chemical reaction like cation exchange capacity. Okay. Disadvantages of the admixtures, you need to test it. You need to figure out if that particular material that you want to mix the soil with is going to be okay. There's usually problem with dust control, and there are also problems with the weather dependency, meaning that after a few years, the benefit of this treated material is gone. It's gone because the cycles of wet and dry, or stuff like that. And there is an also very big problem, at least on expansive soils. I'm going to go a little bit more in detail on this one, is this when we have sulfate-bearing soils, okay? So just always think that when you're going to need to stabilize or just, add some lime into your soil, or, any product that has calcite in there, you need to, first of all, check for sulfates on this soil, okay? This is very important. I'm going to show you why. Hydrated lime, this is one very well used, at least in the United States, for clay materials, right? For this expansive soils, the norm is not to use cement. We use lime, okay? Lime for that, for CH and CLs, and for any clay gravel or clay sand that you're going to find in there that you need to do. Why? It will reduce the plasticity. It's going to make the soil less sensitive to moisture changes. It's usually considered when the soil has a pI of greater than 12, they don't even measure swelling. They just They just go and stabilize. Not a good practice, but that's what they do, right? If they have the money, fine, just go ahead and do it. But usually, may result also in frost susceptible mixes because the soil is going to behave a little bit more like a silty material, okay? So you probably are be fixing one problem, but you might be, making another problem around. The Portland cement is more commonly used in non-plastic soils, all right? So you got gravels, you got, no gravels, but, soil that I need to stabilize more on the granular side or on the less clay material, then we use cement for that. This one is also a guide that is found on the Australian procedure for design guides, for design of pavements. And this one is pretty much a summary of the type of the soils that you can use for a different admixtures that you have in there. For example, cement and cementitious blends, it's usually suitable for soils that has a more than 25% passing, but the PI is less than 10, for example, okay? But mostly it's used for those that have less than 25% number 200 passing, but so you can use it in most of them. Usually it's not suitable for soil that are plastic, all right? Greater than 20 or so. So this kind of charts is going to help you, okay, at least to do a preliminary guess of what is going to be the best thing for you today to do, depending on the soil type that you're going to find. Here is same, the lime. The lime is used for the clay materials. Bitumen is usually for, more granular material or less, passing 200, and so forth. So what is the chemistry of the lime stabilization of the soil, at least for you to understand what is a problem with the sulfates in here. When you put lime, whether in any form, to the soil, there are three main chemical reactions that are going to be occurring there, right? The one is an immediate reaction which is the cation exchange capacity, right? Cation exchange and the flocculation of capacity. Cation exchange and the flocculation. What happens is you're adding calcium ions, okay, that will make, from the lime, that will replace cations that are like the sodium, monovalent. So the divalent is going to be replacing those which are weaker on the soil, right? So you're going to be making more absorption into the clay surface. This will reduce the diffuse double layer that you have in there because it's going to be leading to flocculation and agglomeration of the clay particles, all right? The result is going to be improving workability, reduced plasticity, and faster compaction for that. Another short-term reaction that occurs when you put the lime on these soils is a pH increase, okay? A pH increase and dissolution of the silica alumina that you have in the soil, okay? When you put lime in the soil, the pH rises for about 13, and at this high alkalinity, the silica and the aluminum from the clay materials will dissolve in the pore water, all right? So this is something that you're going to have in there. Another long-term reaction that you're going to have is a pozzolanic reaction, right? And it's basically this dissolved silica and aluminum that is now on your water, pore water, will react with the calcium, okay, that you just add from the lime and form cementitious components, right? This is the cement stuff that you always do, right? So, calcium silicate hydrates and calcium aluminate hydrates, this is what you form. And these compounds are similar to pretty much a Portland cement kind of stuff, right? And provides long-term strength and durability to the material, all right? So these are pretty much, in a nutshell, what the chemical, situation is happening when you do put lime in the soils that are expansive. In summary, the lime stabilization first is going to be improving the soil plasticity and workability through the cation exchange and the agglomeration or flocculation, and later will increase the strength because of that pozzolanic reactions from, to form cementitious soils. All right. How much do you put? You know, it depends on the city procedure or the state procedure or the, you know, whether you are here or there, whether you are in the North India or South India, right? So basically, it all consists of what is the best practice or the most, you know, what the experience of the groups in engineering have had. But if you check most of the procedures that are done for that, whether local or, you know, state agencies or national, is about the application of about 1 to 3% of hydrated lime toward the drying of the soil and get the compaction going. And again, there is no gain of a structural capacity of the pavement with that kind of percentage that you're adding to this, right? When you use in the stability of expansive soils, when you do a test, sometimes, you know, you get more than 3 to 5% of free swell on that, you know, odometer test that I show you, the 45, 46 ASTM, and then you just go for that. And again, the treatment depth is limited by the construction equipment. You know, usually there are 2 to 3 feet that you can treat. Okay, it's difficult to do more than that because of the equipment, right? Because of the mixing that you're going to need for that. Okay, so now you see that you can, you know, replace the soil, just get rid of it as much as you can, and then you can do 2 or 3 feet of, you know, mixing with this lime and trying to improve it. Okay. Problems with lime stabilization. Certain soils have been seen to produce soils that are prone to kind of a reflective fatigue cracking. All right, and there's been some documentation about that, and may produce also soils that are highly susceptible to frost heave. All right, and it's basically, like I said before, the soil is going to start behaving more like a silty material, right? It's gonna have, if you allow some water going on in there. And this is basically happening if the curing period that you got is not enough. Okay, if you had a very nice stabilization, probably you're going to be okay. But if you don't let this cure enough, then you may have problems with that. Lime should be between 3 to 8% of the dried weight of the soil. That's another formula that I found. And mix should have an unconfined compressive strength of greater than about 50 psi within 28 days of curing. Lime stabilization methods, they call for a minimum compaction of 95% density. As per the ASHTO T99, which is the ASHTO to do your granular-based material and cement-treated soils. Okay, this one again is in Rollins and Rollins. There is a nice table in which you're going to see for every type of several soils that they have been dealing with, what is, as you put more lime content in there, how much you're going to be improving your liquid limit, your plastic limit, and your PI. Okay, so that's why we know there are some soils. So obviously, if you can do some testing in the lab before going into the field and trying to figure out what is your optimum lime, you know, so to stabilize the soil to a point, right? So you don't go too much on that, spending more money on that. And also for the QU, the bearing capacity on that, or the unconfined compressive strength. So there's some information in there for you to see. And you can see here, for example, that you have soils in here that when you put, let's say this one is a high plasticity clay from Illinois, it's called Brico silty clay, and you have a PI of 29. When you put 5% of lime, you ended up with a non-plastic soil. Okay, so this is the kind of improvement you're going to get. So there are some dramatic improvements on that for sure. Okay, this is the effect of lime content on the soil properties. This is usually, I give my students a question on that. It's not on your exam today, okay? It's not on your exam, but basically how the strength improves with the adding of lime content, right? Okay, so basically the strength will improve. The length change, which is the shrinkage behavior on the linear shrinkage test, is some simple test that has been done also. You know, you see the dramatic change on that. the swelling also is reduced, the swelling pressure is reduced, the liquid limit is reduced, plastic limit a little bit high, and therefore the PI goes down, okay? So there are all these, and you can check your soils and figure out what is the lime content that will just stabilize your soil so you don't go too much. The durability of the lime soil mixture, and I focus on lime because this is the main mechanism that we use for expansive soils, right? That's what I do that. So that may be affected by environmental factors. Water is one of them. You know, most live stabilized soils retain the strength and the long-term condition, but when they get exposed to water, there has been reports that there is a poor strength retention for stabilized soils exposed to these soaking conditions, right? Freeze-thaw cycles, you know, it seems like when you do freeze-thaw in several years, you do have some deterioration of this material. What I'm saying is, if you're going to be cement stabilizing something, you may think that this is not going to last forever, okay? It's not going to last forever. If you have any of these conditions that can be improved, so you may consider that. Leaching of the calcium, usually you got the calcium on this one, and that's going to decrease obviously the cation exchange capacity that already occurred, and basically there is a reverse in the beneficial of the reduction in the plasticity of the soil. In other words, the soil will gain plasticity again, right? Carbonation caused by the combination of the lime and atmospheric carbon dioxide, and that makes to form calcium carbonate. The calcium silicate and the aluminum hydrate, and also reverts to the original silica and aluminum form when that happens. And sulfate attack. Sulfate attack, I'm gonna just give a dedicate a slide to that one. This is a very important one. You have sulfates that are present in the soil water. All right, some soils do. Some agricultural soils, for example, have a lot of sulfates because they were used for the plants, and now these areas are now into the urban development, and there were a lot of sulfates left behind on the groundwater and the soil water around. When they combine with the calcium that you're putting in there from the lime or the aluminum from the clay minerals, they will form ettringite. Okay, this and actually vermiculite is the other one. This one has a volume change that is more than 200% larger than that of its constituents, meaning that you're trying to fix the swelling potential of a soil, right? But if you have sulfates on the soil and that sulfates combined with this calcite, okay, you can form a worse problem in there. Okay, as a matter of fact, in Arizona, about, I would say 25 years ago, we were just expanding upon the north side of the city, in Phoenix, and basically there were a big urban development going on in there, and one of the companies was hired by the local authorities, the county authorities, to make all these roads. Those were all on expansive soils, right? They were just street roads on expansive soils. Basically, they go over there and they spend a lot of time and money, and they build the county, and a year later, all of these roads are absolutely cracked and crazy. All right, so the soil is going up and down, a lot of cracks all over the place, longitudinal cracks. So what happening here? The asphalt mix was okay, the formula was okay, the thickness were okay. When they figured out the soil had a lot of sulfates, and they did not check for sulfates, all right? I mean, that got bankrupt, the company got bankrupt. Obviously, they have to pay back, redo all of this work. And the sulfate test at that time cost about $100. I mean, nothing, right? Nothing. So it's just a simple thing like that, okay, will bankrupt a company, your company. So you need to be very careful with this. Sulfates are, and everybody put lime on these soils, everybody. So you need to make sure that you don't have, Vegas also had a big problem on that one a few years ago, like 6 or 7 years ago. I mean, I'm talking about now. I'm not talking about 20 years. We have experience with that. We know what's happening, and people are still making mistakes like that, okay? We engineers making mistakes like that. This is a massive irreversible swell in our core, okay? So the road or any light structure put in there is going to be damaged. It's difficult to predict the combinations because, you know, you may have sulfate contents and stuff like that, and they may combine. If they're soluble, fine, you know, they're going to be more prone to combine or not. So it's difficult to know how much calcium is going to be forming out of the lime. So you better take provisions about that. So if there is a suspicion of possible sulfate attack, okay, the lime stabilized soil should be tested in the laboratory before that. Okay, so you need to test for that, and basically it's going to be introducing water into that to see to make the sulfate soluble and see what's going on, right? So there are some tests available for you to do to make sure that that's not going to be a problem. As for cement stabilization, I'm not going to talk much about it. A low cement contents, the product is generally termed cement modified soil. That reduces also the expansivity, reduces the frost susceptibility. And at higher cement contents, the end product is also termed soil cement or cement treated base, CTBs, right? That's where you see those in the report. Subbase or subgrades. These are the proper mixing for a CTB or cement treated base. I'm just putting here, you know, some of the considerations for you to do. The PI should not be high, okay, should be on the low side if you want to use that on expansive soils. Again, the king methodology or admixture we put is lime, but we got also people putting cement on that, right? So use it if your PI is less than 20. If the passing number 40 is greater than 45, this is, you know, what the ASTM standard said. The cement content should be somewhere between 3 and 10% of the dry weight of the soil. Again, all of these should always have, previous laboratory tests for you to know, how much you can put in there. Unconfined compressive strength should give you 150 psi or more than 1 megapascal within 7 days of curing. The CTB should be compacted to a minimum density of 95% of gamma D max, as per the ASTM, the M134 for CTBs. And usually you use type 2 cement that has greater resistance to sulfate attacks, or sulfate resistance, or type 3 cement has greater strength. So you need to play with whatever cement that you're going to need to use, right? Durability. Organic matter and sulfates are the enemies for cement treated material, okay? Tests must be conducted prior to use. If you have organic matter and you cannot avoid that, some inhibit the hardening process for that, so just test. There is a test that is done, and I brought this one in here because I had a question in here about organic material that you're gonna need to do some stuff on this. And if the pH of a 10-to-1 mixture by weight, okay, of the soil and cement is greater than 12, that's what I found. After 15 minutes of mixing, then the organic matter should not be a problem. All right, so you can just deal with that if you, but you need to stabilize it, of course. All right, you need to stabilize it. Sulfates, again, I already talked about that, but the resistance to sulfate attack differs for cement treated, coarse grain and fine grain soils, and is a function of the sulfate concentration on your soil. The use of cement for fine grain soils containing more than about 1% sulfate should be avoided. There are tables about the parts per million of sulfate content that you need to avoid, or when the susceptibility to sulfate attack is higher or lower. I didn't bring them in here, but you may have some of those too. Here is a step, and probably I'm not gonna go, probably, yeah, why not? Still time. The genetic and mixture design, and this is just for your information in here, and how these professionals do their work, okay? Usually, and again, this one is based on experience, based on many years of trial and error. This is, ended up being the standard for the city or the state, okay? So you classify the soil to be stabilized. You usually do grain size distribution, NPIs, prepare trial mixes with varying percent content. If you are using lime, you select the lowest percent with a pH of 12.4 in an hour, and that you can get. And if you're using cement, use a table to estimate the cement content requirements, and there are tables available for that. If you're using asphalt, there are equations and tables in this particular rollings, okay, that I had the reference at the end of the lecture in here, in which you can estimate the quantity of the cutback asphalt that you need to use. So all of them there are things that are available. Right. So the next, once you prepare the trial mixes to see how this mixture is going to be working for your soil, you develop moisture density relationships for the initial design of the treated material. All right, that's going to go in there. Then you prepare triplicate samples, and this is something that payment people do. We don't do triplicate. I don't know how many samples you do, but usually we don't do many, right? You duplicate samples because it takes a lot of time. But the more samples you do, the better, and cure specimens at a target density. Determine the index strength that you're going to have. Usually it's an unconfined compressive stress. You just break the sample and figure out what is the unconfined compressive strength. I show you a couple of target densities before, but there are standards for that depending on the use of the soil that you're going to have. And for the asphalt, which is out of our thing, they do Marshall stability. Payment people in here, I'm not going to get in there. Determine the resilient modulus for optimum percent admixture, okay, and perform test or estimate using correlations, like we saw it before. And I shouldn't put chapter 5 in here, but lecture 5. And conduct a freeze-thaw test if the regional is, you are in a region and is required when you have this mixture. So these are pretty much what you need to do, or the considerations that you have to do on that. Again, there are manuals that we're going to get you into that, but I wanted for you to introduce to something that probably you haven't seen before, okay, if you need to talk about, if you need to work on a payment geotechniques problem like that, okay? So with this, I hope you just get into this without fear of, there are information in there for you to check. Do you have any questions for the cement and mechanical stabilization before we get into this geosynthetics? All right. So much time do you having here? 10:30. What time did we start? We started at 10, right? So I got 20 minutes. Okay, we're doing fine. Geosynthetics. Any questions? Any questions on the online audience? That was clear, huh?
Professor, is carbonation a problem in cement-treated bases? Is carbonation a problem in cement?
Yes, and yes, it is. We mentioned that, yeah.
From what I read, usually you have Portland calcium hydroxide in a cement-treated base, which deposits because it needs sufficient volume. Calcium hydroxide, so it deposits on the surface of aggregates. Mm-hmm. So that is why when we do a split tensile stress, the interface is along the cement matrix and the aggregate surface, because that's the weakest plane. So when carbonation is happening, this calcium hydroxide converts to calcium carbonate in the presence of calcium dioxide, right?
That's correct.
So we are improving that plane. Mm-hmm. So that is a benefit, right?
Yes, yeah. That's, that's correct. Well, the carbonation occurs for sure, right? When you have that, when you have at least this thing. But yeah, there are ways to improve it, right? To improve it. And if you catch it when that will occur, which is going to be in the surface, right? Then you can do something like that. I'm not familiar with that kind of improvement for doing that, but certainly it's something that you need to consider on the design. Okay. And what you said is this is what exactly happening. Yeah.
Prof.
Yes, sir.
Good morning, Prof.
Good morning.
Actually, I would like to ask the question further, like when we have to conduct a freeze thaw test, so for which test we should go for conducting the like how to measure the for freeze thaw test the improvement, how we could say the improvement has been done considering the effect of lime or make in this cement treatment.
Yeah, there are methodologies and procedures to do the test prior to try the treatment in the field. How do you recognize if that is not gonna? It's not that it's gonna be improvement. Is what you're trying to recognize is that if freeze and thawing cycles are not gonna be a problem to your stabilization chosen technique, right? That's what you need to find out. So there are, indexes when you said, okay, once you have that, if we have freezing and thawing, you subjected there is methodology, I didn't bring them in here, that you're gonna be doing that, submitting to freezing, thawing, okay? And they're gonna have some indexes in there that said, okay, the water when you're thawing, how this, and it's usually, I think it is with the unconfined compressive strength, okay? So basically you do several, samples, and you submitted this one to different cycles of that, and you measure how much reduction in the unconfined compressive strength after a certain number of cycles, okay? So that's exactly what I think they do, but I didn't bring the methodology. Does that answer your question? I think it's the confined compressive strength, yeah. All right?
Hello.
Yeah.
Here.
Hello. I just didn't listen like that.
No. How sensitive is this method with respect to the temperatures, ma'am?
Temperature, well, freeze and thaw is a problem due to temperature, right? Is the temperature per se that brings the soil to freezing and thawing. So admixtures are prone to fail if you submit them to changes in temperature, right? But this is pretty much that. Now, if you're talking about stabilization when you don't have freezing and thawing, but you do have expansive soils that go into cycles, or a place that goes through cycle of high temperatures and low temperatures, I haven't seen any problem with that. Unless, the problem is the moisture ingress, not the temperature for that kind of stuff. But obviously, if you got into the lower temperatures, that's going to be an issue.
Excuse me, ma'am.
Yes.
So, I have two questions.
Yeah.
One, like in India, we have a practice, say, when we are using CTB. So, the resilient modulus of CTB, we calculate using the unconfined compressive strength. Empirical formula is there.
Mm-hmm.
Now, for same, say, any soil is there, and we have used some admixture, chemical admixture, and the soil got hardened. Now, it's UCS.
And the soil what?
Soil is hardened a bit. So, it's, you can see UCS is improved. Unconfined compressive strength is improved.
For expansive soils.
Yeah.
Okay.
For that matter, we will take expansive soil.
Mm-hmm.
So, basically that unconfined compressive strength of the subgrade has been improved using the admixture. But in our say KNPEB or any software we are using, say linear elastic theory which uses, so it takes a resilient modulus for the sake of calculation. But UCS will give you compressive strength, right?
Right. Mm-hmm.
And we use that empirical formula for the resilient modulus.
Do you think it's correct?
Yeah, so that resilient moderation is not correct.
Exactly.
So how to incorporate that?
Well, I'll have to check, but I'm very sure there are correlation between an unconfined compressive strain. You know, DCP, dynamic control, no, this is dynamic, but there are some measurements of strain like CBR, right? So I'm very sure there are ratios that you can get between the unconfined compressive strain and resilient modulus. That's the best we can do on that one. If you don't do resilient modulus, the model or the program that you're working on asks for resilient modulus, usually you're going to have to use a way of correlate the unconfined compressive strain you get with the resilient modulus. You just can't use it, you know, you just can't just go and put that number in there. You need to figure out a correlation between that, okay? Like we did for the CBR. I just don't find, and I'm trying to figure out if I know of any of one of them. I'm very sure they're available, because this is a very common practice for that. But for the latest models, we're using resilient modulus, right? More than a strain parameter that we used to do before. And you know the reason now, right? Because the strain parameter is only a function of your octahedral stress, and then you don't have that, it's not a good thing. It's just the strength, right? The deviator stress. Excuse me, deviator stress, which is the shear strength of the material. So it's not a good measurement. It's not sufficient, I would say. Okay, it's not sufficient. So I'm going to try to find out a correlation. You know, let's try to find out a correlation, because you should just not just put the values right there. All right, great questions. So let's go. I'll talk a little bit about geosynthetics again, and those are very general considerations, but I think it's important for you to start into this world if you need to go this route of improvement of the soil with this mechanical base stabilization program. So you should be able to describe at least 2 geosynthetics that can be used in pavement applications. You should be able to list at least 5 pavement applications involving, geosynthetics. Itemize the geosynthetics functions that are involved in 3 pavement applications, and explain 2 pavement applications involving, geosynthetics. So that's some of the objectives on that. I mean, this is where I'm going right now with these general considerations. Okay. So I usually bring to the class a big bag of geosynthetic samples for you to check. I didn't bring them here, right? So I hope you've been able to touch them and to see them, and just, if not, I recommend you that I'm very sure there are going to be places where we can, ask for samples. I don't know if Professor Bharat has some samples here. Great. So you got the samples in here. You've been looking at that before, in improvement. But basically, we do have, I kind of, we just put it in different categories. Geotextiles is one of them. You can have them being woven or non-woven. I'm very sure now understand that you are familiar with that. And geogrids as well, okay? So we do have also the geotextiles is a textile, it's a fabric, right? And you can see pretty much when they're woven and when they're not, okay? They're just put together like that and placed out. Most blend, that's you're going to have in there. You also have geocells, and geocells are very interesting. If you're going to this congress or have this, you just basically open it and fill it up with soil, and then you just basically make a big layer, right, or a stabilized material being that way. Geocomposite drainage products like wicking drains. Basically, you do have geotextiles and something, but then you have kind of, I'm going to show you in a minute, some, wicking elements or fibers in the middle that you can just, get higher permeability for the wire to get out of it, okay? So that kind of a composite material. And erosion control products also, you can just, put a stuff on top of your slope and being able to just protect from erosion while you still can let the vegetation to grow, okay? So there are many of them, and everyone has their own specifications and used for different applications. So what are the functions? What are the functions of geosynthetics in pavement systems? This is scored in 1998, and basically we use them for these particular functions, okay, in payments, right? The first one is going to be the separation. We talked a little bit about of that a little bit earlier, and this is basically when you put this one between the subgrade and the aggregate base in paved and unpaved roads, right? And airfields also you can do that. Or between the subgrade and any ballast that you're going to have for railroad systems, right? This is also used on this kind of application. Or between old and new asphalt layers. So you just put them in the middle, and you're going to see that one in a minute right here, right? So separation, reinforcement also of weak material will be our second function for the geosynthetics. Those are different, you see, and that's what you need to think about first, okay? What is that I want my my geosynthetic or my geogrid right there? What do I need, okay? So, and this one, then you start getting into that. I think if you understand or if you know your problem well, the first thing you need to know is if you need separation, reinforcement, filtration or drainage, okay? That's the first thing you need to get when you're using geosynthetics. It's not, okay, I want to reinforcement for what? What do you want to do, okay? What is your final goal? Okay, so reinforcement of the weak materials, usually you put it over the soft soils for unpaved roads, paved roads, airfields, railroads, construction platforms, etc. Reinforcement, usually you can reinforce between asphalt layers. You can between the asphalt layer and the granular base. You can do that one between the base and the subbase, and you can do it between the subbase and subgrade, okay? Wherever you need the reinforcement, you can put that one. Filtration beneath aggregates base, for paved and unpaved roads, and also for airfields and railroads, and this one use the filtration right there. And separation, like we saw that one, right? This one is right there. And the drainage is an interceptor for horizontal flow usually, and drain beneath other geosynthetic systems if you need to do that. Right? So, and that also can be put right below the surface when you don't want the water close to your asphalt pavement, okay? Or you can put it on top of the subgrade so to get the water out when it needed before it gets into that subgrade. So what are the applications of geosynthetics on pavement structures? Again, the first one is probably the mitigation of reflecting cracking, and this is when you start putting that one between asphalt layers, okay, one of them. And basically you just get all these cracks in there and you just want to resurface, right, to eliminate those cracks. Well, even if you resurface with nothing, probably what you're going to happen is you're going to get the reflective cracking showing up again in a couple of years, right? So basically you want to avoid that, or just to get the length of the maintenance a little bit longer, and then you just use it for mitigating reflective cracking. Separation of different materials, stabilization of the road subgrade and granular bases, and improvements of drainage. Okay, so these one are the applications for the geosynthetics on pavement structures. Mitigation of reflective cracking, I've got a couple of slides in here for you. And again, we can mitigate cracks that are alligator cracking or are longitudinal cracking or fatigue cracking. Again, the reinforcement for that is going to be put with thin layers or between the asphalt layer and the granular base material, right? Just get like a barrier for that propagation of the glass. If you got a cement treated base, also they might get cracks, right? They might get cracks and they will reflect on your asphalt. You don't want this to happen, and that's why we just start getting into, putting those to avoid that, okay? The problem of reflecting cracking in the asphalt overlays, is it happens, again, it can happen because of shearing behavior, okay? You got all these cracks going on in here. Or just the bending, those wheels are going on and they're just bending some and just getting into the cracking, or just basically thermal cracking as well. Okay, you got temperature changes and you start getting into the thermal contraction and dilation that will create a problem. This one is, for example, a typical reflective cracking in asphalt overlay. The thermal cracking, you're going to recognize them because they don't go longitudinal to your pavement. They're going to go transverse. They're going to go transverse. Okay. When you get the transverse cracking, you say, okay, this is a thermal problem in here. Okay. When you get the longitudinal cracking, you just start checking into the expansive soils or some other, a failure mode for longitudinal cracking. So again, you just go ahead and, you got all this crack pavement that you need to, rehabilitate. Before you put this one, then you just create the asphalt reinforcements right in the middle, right? So you to avoid that all these cracks will just propagate upwards. Okay. Mechanisms that are necessary that you identify in order to use those geosynthetics on pavements. Okay. Again, you need to figure out if you want a moisture barrier, if you want a stress relief, okay, or if you need reinforcement. All right. The geosynthetics moisture barriers involves mechanisms like minimizing the water infiltration and maintaining the low moisture in underlying layers when you don't want this change in suction to happen too wide, right? Because then you're going to get that problem on volume change. The stress relief involves mechanisms of releasing the energy of the crack propagation. This is a typical case for that. And the third one is the reinforcement mechanisms, which is the distribution of all those strains that you're going to get from your traffic into a wider range, okay? So development tensile strength that keep the confining of the underlying damage layers is important on this one. And we're going to see that in a minute, okay? I've just brought, because it's good, usually we as geotechnical engineers, we don't get into the construction side of the job, which I think this is the fun part, so I brought a couple of slides in here how they do that in the field, but certainly there are many literature that you can see the steps that they use in construction to do that. So first of all, they need to prepare the surface for the pavement fabric that you're going to be pulling. Usually is miling the asphalt, okay? Miling is basically you scarify and you take few centimeters of this one, so you create a rough structure in there. You dry it and you clean it, vacuum, free of material. If you have cracks that are larger than ½ inch, you should be filling them with some material. You just don't want to just put the stuff on top of it. Then you just apply the asphalt sealant. There is a tack coat that you get. It's just kind of an oil that you go ahead and do it. And this is nice. We got every year by November we do have asphalt material. It's called pavement material conference in Arizona, and I'm always fighting to put a geotechnical section into this one, right? Because it's everything about pavement that nobody talks much about, geotechnical transport. So we put this one. But the nice thing is, with geotechnical, we are able to go and see this kind of, demonstrations in that. So if you have some demonstrations around, if you see anybody paving or putting geosynthetics, that's something that. Another thing that I do is I keep my hard hat in my car. So when you see something going on in there, you just, put the hard hat and ask permission to get into the place, and they usually do it, okay? They usually let you go over there and see what's going on in there. So that, being curious about that, you learn a lot of stuff, okay? Asphalt cement, you put, the tack coat, and then you just install the pavement geosynthetics on top of the tack coat, okay? And basically they can do it with a mechanical means. They have machines where you just roll the stuff. It's pretty sophisticated to me, I think. Or you just do it by hand, right? A couple of guys, and just, you need to be very careful not to have wrinkles and things like that. So it's a little bit of art on this installation to do. And the last thing is they place the asphalt concrete overlay on top of that, right? So you just, put the asphalt overlay in here, and usually you need to put at least a minimum of 1.5 inches, okay? Because of then your traffic is going to damage your geosynthetic if you don't do that. Anyway, I wanted to just bring this one in here, and then, there's some testing for the cracking, and it shows that, if you do have the cracking before, then you just have the cracking, disappearing, at least for a while, when you do have this geogrid placed into the asphalt layers, okay? So that thing works very well. And I bring this in here because usually geosynthetics have been an area when it hasn't come from the academic side to the practical engineering, has come from the practical engineering. They start making a lot of money, and now the academics are looking at that and said, okay, what's going on in here? What kind of mechanisms we have, right? How can we improve that? So they're way ahead of us on this. Separation application, it's an easy thing, just I'm not going to go much on this one. You put it between base and subbase or subbase and subgrade, and basically it eliminates the problem when you do have, gravel getting into your, soft subgrade, or the subgrade getting into the, just into the fines and just basically, damaging your asphalt drainage system, your layers that have drainage, right, on this one. So this is important. We have made, and I'm very sure you have, over there, the granular-based material cannot have more than 10, 12% of fines, and some of them have more strict than that, okay? They should not have more than 8% or, to 10% of fines, right? So the problem is when that granular material is sold to the state to do the roads, they sell it, and they sell it without washing it, right? It looks good. Well, then if you wash this one, you can see that those material has about 16%, okay? 16%, because when they check it, they don't wash it, right? So we did a lot of testing on resilient modulus and the moisture accumulation and the suction accumulation of those fines, and it's a tremendous problem that you do have if you got 3 to 4% more fines into those granular-based materials. So you want to avoid fines in your granular-based materials, all right? Arizona has no rain, all right? I'm talking about 6-7 inches a year, okay? Just multiplied by millimeters here, right? It's very little amount of water, okay? But you go over there and you core through a pavement, and you see water in that granular-based material. Granular-based material that is not, 40-50% degree of saturation or less, the granular material that has 85-90% degree of saturation. So the problem is the moisture that is going for, because we do have huge temperature changes, right? We can have a sweater during the evening, but we have 40 degrees during the day, right? It's a desert. And basically those changes creates a thermal gradient that brings all this moisture, right, from whatever place it is that it has to be, and that is being retained by the fines that this, granular material. If you have no fines in there, the water is gonna, it's not gonna survive right there, right? It's gonna get away. So those are cases that you need to take into account, that this is what, it could damage your road. That. Separation already went through that, or without geotextile, and with geotextile we just, the aggregate intrusion and the soil pumping will be eliminated. And the longevity improvement, there are no procedures, there are no design guides that include the benefit of the geosynthetic per se, at least not official in the United States, okay? Do you guys have any of that for those working on the field? There are no, okay? So there are ways that people have tried to measure the benefit of that, and I'm gonna go that into the second hour a little bit, in more detail. But this one is pretty much, what we have done for that. And this one is how to figure out how to improve it. This is Alcari. And basically what it does is just, trying to figure out that without geosynthetic and with geosynthetic, which one is the It's not. The amount of easels that you can sustain on the road, okay? Equivalent easels means the amount of 18,000 pounds wheelers, right? Equivalent to those that you can just get into your road, right? And this is the W into the AASHTO payment equation. And basically you can see the benefit as you go, as you have more load, you're going to have more benefit. All right. So course like this you can find, and paper like that you can find. Do you guys have any questions with that preliminary thing on the geosynthetics? I hope you guys learn and I get you interested in some of that stuff, in some of these things. All right, 11:06. So I'm into your, break, tea break. Yes?
Sorry, Prof.
That's okay.
Actually, I have one question. Is in terms of comparison, which ones perform better in terms of stabilization technique for the subgrade soil, which is subjected to either zero temperature or freeze cycle? Means if we are comparing geosynthetic or the chemical techniques as a stabilization technique. Considering to means this is for both roadways and railways, as both goes through the moving load or the cyclic load repetition cycles. So which one performs the better? Can you please explain?
I've seen many applications going towards the geosynthetics. Again, the mechanical main way to deal with frost, conditions is being to get this amount of gravel high. Okay, and that's a mechanical way of doing this. So if that doesn't work, I've seen, or at least I've seen people trying to do the analysis, the economical cycle analysis to see what happens if you do that, or what happens if you start putting geosynthetics and reducing the stuff. So there are many studies going on that, and it seems like a geosynthetics is not a bad idea. It's not a bad idea, because getting granular material of a certain quality in many areas is not easy, okay? There are some areas that have a great quantities of material, but some areas that have to bring it from far away, and that creates an extra cost to your construction cost. So at the end of the day, it's going to be what's going to be costing less, right? And if the two of them work, what's going to be costing less? If you have gravel availability, probably that's the way to go, mechanical stabilization. But if not, and if you're going to be more cost associated to that, then probably stabilization with geosynthetics is going to be the right way to go. All right, that answers your question? Okay, you're welcome. Any other questions? I guess I'm very sure we're going to have a lot more questions on the break, so let's go ahead and come back in 20 minutes, 25 minutes. All right. Yes.
I am from railway, so we want to stabilize the railway embankment. Which method we should prefer during running train without suspended of track?
Okay. What happened with the ballast, right? That the material that you use is a little bit different from the one that we have, right? Apart, if we're talking about subgrade stabilization soil, then the lime-treated soil is the way to go, and things like that. If you are in an area when you have frost heave, probably gravel, increase of gravel depth will be the way to go. But if you're talking about how the stabilization of the ballast by itself is going to be, right? The problem with the ballast, what I understand, I'm not expert on that. There is a big group in Australia working on that. It's great. And basically, what happens is the ballast trying to spread out, right? Trying to spread out, and basically just lose the strength because of that lateral spread out. Okay. In that case, geogrids. Now, geogrids below this one will allow for the interlocking of the particles. Okay, and we create basically a way to just avoid that straight out. Okay, we're going to see that a little bit of the mechanism in here. But that is what I understand it's been working good on that. Anybody has any better idea?
Axial geogrids have been used in railway mappings
Yeah, the geogrids.
to reduce the effects of mud pumping,
Mm-hmm.
and also as a separation layer and as well as drainage layer.
Mm-hmm.
Reduce complication of geocristals and geogrids. In some other railway, they put no also in fact.
Mm-hmm.
They've been using it.
Yeah. So that will be, yeah, to me a very good. Geosynthetics are working fine. I mean, just we need to realize more the mechanism and how to include into the design procedure, right? How to quantify the benefits of doing that, so we can compare with traditional procedures. I think this is our job, right? Our job in the universities, more than anything else. Tensar, Solmax, all of these companies that are very good at geosynthetics, they're geosynthetic companies. They have their own design procedures, right? And they're free. You go to Tensar and you download Tensar. I don't remember the name, but it's you get it for free. And it's incredible. It's actually very nice. They said, okay, I do have this frost action, and you're going to see the granular base increasing in here. They have a very nice animation of that, right? Well, you go behind these things. Some of them are mechanistic, found, but some of them are very empirical, that. And they not only do that, they change your asphalt, how much asphalt, granular base, all of this, when you put the geosynthetic or without geosynthetic, and you give them the comparison of the prices below. What costs you to put more gravel in here or asphalt in here? What costs you to put this kind of one geogrid or two geogrid layers or something like that. So it's amazing the job that they have done on that. And there are some of them that are very rigorous on that, some of them that is just empirically, right? Empirical. So these are the stuff that we need to check, in order to improve, right? Improve, or just trying to figure out if what they're doing is mechanistically correct.
Excuse me, Prof.
Yeah.
Again, this side.
Sure.
I'm just adding to the second last question that the person asked about the railway embankment. As you correctly said further, but last we can put a geogrid. But what if it is subjected to railway embankment resting on the soil?
Subjected to what? I'm sorry.
Different drainage condition. Subjected to what exactly? So what if means there is something some deterioration hasn't happened in the railway embankment? So how to mitigate that particular? Is it the vertical drains is going to be affected in that case?
Well, the nice thing about ballast and drainage is that you do have a very low suction values for ballast, right? You got granular material in there. They don't retain water. So it's good because they drain easily, right? Now, if you have water in there and you don't want the water to go into the subgrade, and you're talking about, okay, we can use geogrids, but if you want to improve also the drainage, there are composites, and there are some that are geogrids, okay, together with kind of a drainage fabric or wicking drain and stuff like that. And there are composites between geotextiles and this wicking drain as well, okay. Nice thing about this, I think the entry value of those guys on the wicking drains are about 75 kilopascals, which is much higher than the one for the ballast. And what happened is that this guy is gonna get the water in, okay. If you put a wicking drain in a clay, the clay is gonna retain the water. So if you had, when you have almost saturated conditions, the wicking drain will work. But if you do have unsaturated conditions, dry system, the suction in the soil is going to be much higher, all right? And basically, it's not going to release the water to your wicking drain. It's not going to release the water unless you squeeze the water out with some other stress component, right? Like, putting something on top or just releasing that. So yes, there are some composite geosystem that you can do. Vertical drains are always work, if you need to, get the water directed to a certain plane, you always, can do some, sand columns or stuff like that when you can get the water in. I think at the end of the day, it's not that we don't have solutions, it's the solution that is most economical for you, right? So I think that's at the end of the day what is not the best solution. The best solution is whatever you can do with less money, right? And it's still right. So yeah, this is my take about the composite geotextiles. I think they might do a good work for this kind of materials. All right, guys. You're welcome. All right, so let's go and have some tea. And we just keep talking on the tea place.
Ma'am, one more question.
Okay.
From mine. Like, what will the effect of aperture sizes of geogrids in the subgrid for? Suppose the basic function of geogrid will be the improvement of the strength, right?
Not the basic. You saw there are many of those, right? There are different functions, right? The strength is one of them.
Yeah, like how it is going to contribute towards the drainage. Geogrids as a part, like
the geogrid has no component on the geotextiles. Yeah. Okay. Yeah. Geogrids are a big, kind of a net.
Yeah. Okay.
Like
if
so, and they're very thin, so they're not gonna make a, a place for you to get drainage at all. Okay. So you're gonna need some geotextiles or something that really direct the water out. Okay. That it has some fabric that will just get those channels out, and they are available for drainage. But geogrid itself is more about the interlocking of the particles if you have granular material, okay, and the distribution of the stress if you have lateral spread out of your materials on the granular base. So this one is like the way we've been using it. It's not about the strength. You don't get a strain. Okay, you're going to see that in a minute. Okay, the bearing capacity. You just change the bearing capacity from a punching local shear failure to a more general failure. That's what it does, pretty much. Okay.
Thank you.
Good question. All right, that's okay. All right, let's go have some tea now. I'm trying to have tea here for the last 10 minutes. No, I'm just kidding. Great question. I have a problem with my, very, I guess, is that okay? Yeah, thank you. Alrighty, let me check. All right, I think we're ready to keep going on our last hour in here before you take your exam. I guess we have lunch after that, and then you take the exam, right? All right, so we're going to talk a little bit more about geosynthetics again on the second road, and I'm going to talk about the subgrade stabilization. I gave you the comments this morning, but we're going to try to get a little bit more into the bearing capacity and stuff like that. For unpaid and paid roads, usually this is what we use them to, for unpaid and paid roads, but also for low volume roads. Although, like everybody's using. This one is a course that I attended, and again, there was a whole day course in GeoCongress in March. So, and Professor Jorge Somber and Professor Tutumlier were the ones that delivered this one. So these are notes from the course that the professionals and academic people took about 3 or 4 months ago. So talking about stabilization of subgrades now with geosynthetics. And again, we talk about the 3 main objectives of that, or functions that we have for geosynthetics on those roads, being the drainage, filtration and separation, and the reinforcement, the third one of those, okay? So when we talk about reinforcement, we don't talk about getting extra strength in there, right? Strength in there. What we talk about in here is the distribution of the stress, all right? So when you do have no geosynthetic, basically it's going to happen that you're going to be limiting, or the application of the load is going to be very punctual, okay? Apply to that one, and the stress distribution is going to behave something like what you see for local or punch shear failure. When you get into induced geosynthetics in here, basically the ones that use these geosynthetics, they claim that what it does is induce a lateral restraint, right? Which allows the stress distribution to be a little bit much better. So now you're not going to have the maximum stress applied to one point, but it's going to be distributed more widely, or more on the width of the road. Okay. So the conceptual design approach, basically you put the gravel or the sand directly on the subgrade, right? The gravel. This is what happened on the low volume roads, or for any road, for God's sake, So sometimes we surface the road with stone screenings or chip seal in order to avoid the dust that this low volume road does. And we do have a lot of low volume roads, and I'm very sure you do too. Okay, you're going to have to deal with those guys in some time. And there are generic design methodologies for unpaved road design procedures, okay? And obviously, if you get into one region to the next one, it's going to be modification to that, depending on what they're going to be using, or the climate they have, and stuff like that. So the focus for the stabilization of road with the geosynthetics is on the reduction of that stone-based thickness that we put on top, okay? The aggregate savings. So this is pretty much our main stuff, right? How much we are able to lower the aggregate thickness in such a way that we're going to be saving money on that. So we put the stabilization lift, then construct the design pavement section using the standard method for pavement design, right? So usually there is no structural support again on these particular pavement methodologies when we use the geosynthetic. And again, the objective is the increase of the bearing capacity of the subgrade that we're going to have in there. These are some of the criteria I found for the geosynthetics in pavement applications, and I think it's been there as, you know, very common criteria for that. When you use it for, depending on the application that you're going to have. For example, if you use it for base reinforcement, okay? For base reinforcements, basically, it's used when the California bearing ratio, again, this one is used by everybody in the world, the CBR value that we talked about yesterday, and how we can relate it to resilient modulus. Well, you can do an unsoak or field condition, means that you get your sample at a natural water content condition, and then you just create, you know, do your CBR testing, or you can soak it, right? Saturated condition, right? When you find that the CBR value is less than 3 or soak less than 1, I didn't bring the scale, but, you know, this is very bad. This is a very bad base CBR, then we call for base reinforcements. Same thing for the subgrade reinforcement. You know, if we had CBR, soak CBR, and soak between 8 and 3, or 3 to 1 if it's soaked, and the separation can be done when we have a greater CBR greater than 8 or greater than 3 for the soak. Okay. Another criteria is the undrained shear strength. The undrained shear strength. If you have an undrained shear strength of 30 kilopascal, then it calls for a reinforcement. Okay. Or also the kind of soil that you got in there, right? You know, this one actually that's what you start with. If you have a fine-grained, wet, saturated soil, okay, of these categories, you know, clay material, clay sands, low and high plasticity clays, low and high elastic silt, organic matter, peat, and so forth, then it's going to call for some stabilization. Okay. This is the FHWA, which is the Federal Highway Administration for United States. This is the criteria that they use for geosynthetic in pavements, right? And they have just this table, and then you have to go through this one and check. And if that is the case, they're going to be requesting, right? So why is this important? Because when they get into this kind of methodologies on analysis, that is going to be the first thing they're going to be checking if the road failed, right? If you were able to do all of these criteria. So basically this, you know, get you away from jail, right? Or away from trouble or lawsuits if you just follow the criteria. If they're there, we need to follow them. Okay. Poor soils. If you got poor soils, like the one that I show you, and you know, this one is the U.S. classification or the AASHTO classification. We talk about A5, A6, and A7, 5 and 6 soils. The low strength, you know, we're talking about undrained shear strengths of less than 13 psi, which is about 90 kilopascals. Our CBR, CBR of about less than 3, or the resilient modulus less than 4,500 psi. If you have high water table within the zone of influence of the surface load, for example, you do your little busyness, can you figure out what is your, you know, load influence of that, and you just decide on that. High sensitive soil, high undisturbed strength compared to remolded strength. This is the definition of a sensitive soil, right? You know, if you have high strength when, you know, it's undisturbed, but when you remolded, you have very low strength, then you have a sensitive material. Okay. In addition to that norm, the FHWA HI 95-038, we got another document that is not a design procedure, okay? I'm just going to tell you like how we work the stuff in here. Again, you have your own procedures in here. And the AASHTO M28806 are some requirements that you have to have in addition to the ones that you got in the FHWA document. And basically, that deals with the characteristics of the geotextiles that you're going to have in there, okay? Deals with the surveyability, I never know how to pronounce this thing, the permittivity, and I want to see a little bit that later, and the maximum up AOS, which is the apparent opening size for that geotextile. And obviously, there are many, many considerations on drainage as well. Okay. Again, stabilization of a paved road or subgrade reinforcement is you are avoiding punching shear and you're trying to get into a more general shear conditions. Okay. So the way this methodology works is the same bearing capacity theory that you learn for shallow foundations, right? So you have to have all these, Terzaghis parameters, right? The NC and gamma and NQ, if I remember well. Okay, so if you have them for undrained shear strength, conditions, for example, there are different sources of information when they said how much you have to modify those NC parameters, right? If you do have geosynthetics, okay? So these again are, based on individual work, individual testing from different authors. Like for example, Berenger said, okay, if you do have an NC value of 3.3, if you put 6, you put 6, actually it's a gain of 81% of bearing capacity. That's going to give you the value, the equation for using on geosynthetic, okay? And there are some other, like the Forest Service, which have done a lot of work because they do have a lot of low volume roads, right? So you're going to find a great literature on that U.S. Forest Service, and they were much ahead of the other agencies. They talk about an NC value from 2.8 to 5, 79% GROT. Talk about a 64 improvement if you put a geosynthetic and Halliburton, from NC from 1 to 1.5, for example. Okay, so these are studies that have been done that give you an idea of what the bearing capacity gain you're going to have if you just put geosynthetics or reinforce the material. Okay, did I bring that again? It's okay. So okay. There are different procedures available for design of roads with geosynthetics, okay? That are available. And they're available for a long time, since the 70s, right? Since the 70s. And there are some of them that prevail, and some of them that have done a better job on improving, the procedures. One of them that have prevailed is the Stewart et al. Procedure from 1977. I'm going to just show you the design criteria that they use for that, and that's what the U.S. Forest Service use and still use. But there are many other ones, like I brought you here the sources of information for you to check. So the Stewart et al. 1997, and this is just to show you how this thing works, like how these procedures get into the practice, is again the concept of bearing capacity theory modified for the inclusion of the geosynthetic, right? That's what we do. The geosynthetic inhibits subgrade strain. That's the main assumption, and that we are producing a general versus a local or punching failure. Okay, so they consider obviously all these load conditions that we had on the road, like vehicle passes, axle configurations, tire pressure, subgrade strength, rod depth, and so forth. Rod depth allowed, right, and so forth. Okay, so for example, there are some limitations to that, like aggregate layer must be compacted to CVR equal to 80, which is a very high, all right? You can use this one as long as the CVR of your aggregate material, right, is 80. The aggregate layer must be cohesionless, no fines on that. Okay, so they allow the use of geosynthetic as long as you do a very good job of not putting any fines on that granular-based material. And the vehicle passes are limited to 10,000 passes, and the drain shear strength for the subgrade should be less than 90 kilopascals. Okay, for that. This is extent. This was a geotextile. This is extent for geogrease also. Most recently for the U.S. Army Corps of Engineering in 2003. Okay, the bearing capacity, again, you are familiar with the bearing capacity equations and theory. Basically, these values are the ones that basically are modifying. And basically, in order to deal with all these loads that you have because of the wheels, they use the typical Business solution to determine the vertical pressure under a circular load, okay? And this been a great deal of research in whether the tire gets a circular load or a point load and an elliptical load, a rectangular load, and you have them all comparing all of this to see what is the best, information we get. Okay, they use circular load, but there are more sophisticated programs that use elliptical load, right? Depending on the tire pressure and so forth. Okay, so this is another deal, and they're way ahead of us because we do have usually, like I said, normal vertical stresses, and they usually use three-dimensional, load point loads for this one and for all the configurations of the traffic they're going to have. Okay, and the bearing capacity factors that were proposed for that, when you have, with no geotextiles, use these values depending on the traffic load and the ruts that you're going to be allowing to do. With geotextiles, use these values so you can see the difference on that from 2.8 to 5 or from 3.3 to 6. And if you have a geogrid with geotextile for CBR less than 2, you can use an NC value for 5.8. So those are numbers that have been established based on some research doing by that, and those are the ones that we use for the design. Okay. These are typical design curves that they use on the Stewart U.S. Forest Service. Basically, this is for the granular material or the base course material, whether you have single loads or tandem loads on these trucks and traffics. And again, this one is for a particular tire pressure. So you're going to have many of those for different tire pressures, for example, right? And this one is for single wheel loads, the single wheel loads. Okay, and basically in here you enter with your bearing capacity and you figure out what is the depth or the thickness of the granular base material that you need to put in there, all right, for that. Same thing you have for tandem loads, and again the contact area is assumed to be rounded. So the tandem loads you're going to have, 1, 2, 3, 4. Okay, so they do all of this analysis with the amount of loads that you got and how this point load affects all of the stuff, and so this is done mechanistically well, and then they put the empirical design procedures like that for everybody to use. This one is another one that I found for the same thing. This one is again the required aggregate thickness and the CN value for different single wheel depending on a different tire pressure, and this one is for higher loads, like for example if you have a truck, full-size pickup truck, or you have a wheel loaders or scrapers. So this one is more for kind of the construction side of the construction stage on your work. So there are design curves like this that are being used in order to do that. Okay, and again they are being done by the bearing capacity equations using Boussinesq analysis. All right. This one is an example of a design stabilization design procedure. Like, okay, so for example, you have a soil that are very bad. It's very bad. It's a CBR of 1, right? Very low resilient modular. Let's say 3,000 psi, 4,000 psi, very low. So, or the undrained shear strength is about 30 kilopascals or less. So you do have that value. You know what is the single wheel load that you're going to have, the number of passes. You're going to be allowed 2 to 4 inches ruts. Okay, so based on all this information, you're going to get what are the what graph you're going to be using for this design. Okay, like for example, then we get to compare what happened when if you put a geotextile in there or with no geotextile, right? So for this one, the parameter to change is going to be the N values, right, for your bearing capacity material and for your bearing capacity theory, and then like let's say if you use a NC value for 3 with a geotextile and the other one for 5.5 for geotextile, so you calculate your bearing capacity here with this, and basically you just go and enter the graph with a NC value of 90, you get about the depth of 475, and these ones are millimeters, so basically it's 47 centimeters of granular-based material. And if you stabilize this one, then you enter this graph in here with a higher bearing capacity, and you find it's 32. So it's, it's 6 inches in there of saving on the granular-based material when you put the geotextile. But this is the level that we have done again, this is, to bring it in here, that we got a lot of stuff to do. And again, this has been, it's been driven by the geotextiles companies or industry more than from the academic world. But this is what we do. This is what they do, right, on the stabilization of low volume roads with geotextiles. Geosynthetic design for subgrade stabilization in permanent paved roads. Now talking a little bit more on paved roads, which I barely touched this morning too. Well, the phase one is going to be your the design of the aggregate thickness with the geosynthetic as a temporary load. And we're going to go into the steps of that. It's very similar to you just saw with the Stewart, okay, example. And the second phase, okay, is going to be the design of pavement considering improved support provided by the geosynthetic and aggregate. So, yeah, okay. So again, you do have two ways of doing that on the construction phase, when you have your, for working the road, or the post-construction phase when you do have the stabilization happening for the design of the road. Okay, this material is Christopher and Wardle, and here are the steps for geosynthetic design for permanent paved road that Christopher is also has been on the geosynthetics for forever, and he does have great literature on that. What are the steps for the geosynthetic design for permanent paved roads? Okay, so I just trying to put them summary of, for you to understand the step that we follow. We're not going to go into a full example or tutorial, but the first thing is you identify, obviously, the properties of the subgrade. Okay, you know what kind of subgrade you're going to have in there, and you estimate if you need geosynthetics or not, all right, if you need to improve that guy or not. Okay, and if geosynthetics is one of your options, then you just follow this. Okay. Number 3, the design pavement without geosynthetic. Just go ahead and design it, whatever the design procedure you need to use for pave. And you say, okay, I'm not going to put any design procedure. What is my chance with that? And determine the need for the additional aggregate that you're going to need if you don't do geosynthetics. Now you determine the thickness of the stabilized or with geosynthetic from temporary road design methods like the Stewart, the one that you just showed. I'm going to be in a minute there. For other figures, Giraud and Han also has another good procedure to follow on graphs and design curves. Determine other parameters, like I said, is not only the design procedure, but also you have to get some extra requirements for that on separation and surveyability requirements, and the structural support last. Okay, so step 1 and 2, you just figure out what is your CVR, your resilient modulus. You figure out if you need to stabilize that guy whether base or grade soil. So already saw that one. The second is, okay, let's design that pavement, right? We know without the benefit of geosynthetic. And I just brought in here an equation that actually is used by half of the world from the Ashton 1993 procedure. This is the most used design procedure for pavement design. And basically it's a pretty empirical equation. And look at the equation here. With this thing, we design a pavement in the world, okay? This one, okay. Before the design guide, the mechanistic design guide, when we put all these climatic effects and everything, that's what we've been doing. And again, this is what a lot of people still do. And even in the United States, we do that, all right? So this is the equivalent, the wheel loads equivalent to the 18,000 psi wheel load. This is a parameter, sorry I forgot a function of what. This is the structural number, okay? The structural number is nothing but that combination of layer coefficients for the granular base, for the asphalt layer, the granular base material, and the sub-base material. And these are the thickness, right? The thickness. And basically, you just solve for the thickness of your pavement when you have those values. And there are some other drainage coefficients of them. You know, this is how we consider drainage. We just put some parameters in there depending on the soil that you're going to have. I'm not going to go into that equation, okay? But this is how we design, okay? So I just want to, you know, to bring your attention into the, okay, this is the structural number, and here the resilient modulus appears, right? The resilient modulus. So it's one number for the whole design of the whole pavement system, right? So basically what you need to do to figure out what is the thickness of your granular base material, let's use this equation, okay? And you start playing, you know, with some regression analysis in order to get the traffic load and the low, medium, of high traffic load that you need to put until you get these guys okay, right? You know, what do I need to do that in order to do this traffic load for the number of years that your road is constructed to? All right, so basically you play now with economics, okay? What is more expensive, to put a lot of asphalt on this one or to put a lot of granular material, okay, that kind of stuff. So there's going to be some required, you can go less than something, right? So this is the game we play with the Ashton 93 pavement design equation. And probably you guys know more than me on that. All right, there are also some, you need to add some aggregate because there are some, we're talking about a very bad subgrade, right? You have a very compressible soil or an expansive soil, and usually some of the aggregate is going to be lost to the weak subgrades, okay? So when you're dealing with that, basically you got a chart like this, and Christopher shows one of them, in which depending on the CBR, you can kind of have a range of values in which you, the percentage of the design thickness, okay, that you need to, that they need to be added due to the aggregate loss to the weak subgrade, okay? And this one is crucial for the geosynthetics, you know, in industry, because this, you know, if you have a very, very bad CBR, you have a swamp in here, right? You got a pit, you got an organic soil, which is nothing in here. You're going to have to add a lot, almost double this thickness of your pavement, right? And voila, here are the savers are the geosynthetics, right? You know, because we'll avoid this thing to go, and you're going to save a lot of money on that. So, so this one, it needs to be added to that. So this is, you know, some of the consideration that you need to deal with. Then you determine the granular material thickness by any of the methods. I just show you one in here, but again, there are several methods available depending on the agency you're dealing with. And basically, you just, you know, check your bearing capacity factors, and, you know, you figure out what is the required aggregate thickness. Then you use all this extra procedure that is not a code for soil retention, for example, and has to do with the type of geotextile that you're going to be using. And, you know, there are, for example, how do you say it, parameters that define the geotextile, right? You know, and how much they allow us to use. For example, if you're using woven geotextiles, the AOS, or the apparent opening size, has to be less than the D85 of the subgrade. Non-woven geotextile, it has an AOS less than 1.8 D8 of the subgrade, so you need to start choosing that. Another requirement is your permittivity and your permeability. The permeability of geotextile has to be greater than the permeability of the subbase, for example, on the subgrade material. Clogging potential has to do with the AOS, the apparent opening size. It has to be, for example, 3 times the D15 of your subgrade. Everybody knows what D15 is. Surveyability, there are 3 classes. I'm going to show you the table in here for you to keep. And it's it has to be a class 1, for example, AASHTO M288. So that kind of requirements also you need to add them to your design. This is, for example, the geotech properties for class 1, right? So there are tables for that, and these are all the data that a manufacturer has to provide you with, okay? When you're considering what kind of geotextile you're going to be using for that, all right? So the grab strength, the swing seam, because some of them are tear strength, CBR punch strength, okay? So ultraviolet stability, and so forth and so on, okay? Permittivity and AOS. And we got this one for different classes, okay? Then we calculate the improved subgrade support assumed for the geosynthetic, and there are different methods to do that, and this one goes back into the FHWA, the way that you should calculate what is the improvement due to that calculation, and one is on the design stabilization, okay? You can use design stabilization lead with some routing, and they talk about some, little, okay, none. And basically it's when you use the bearing capacity of 5.5 to 6 and no allowance provided for the structural support, okay? So he said, you're not going to give me any support from that guy, right? But I allowed you to work on an NC value of 5.5 or 6, and you just make your calculations. The second method is the design stabilization, design stabilization aggregate with little or no routing, and then you go for an NC of 5 and use an equivalent subgrade support of a CBR3. So you said, okay, this one is going to be giving me some support on that. Or the third method is evaluating the equivalent subgrade support by performing just falling weight deflectometers. You just go over there and figure out, okay, how much you gain out of this procedure, either with a falling weight deflectometer or with a light falling weight deflectometer. Okay. So this is that, you need to assume or you need to measure what is the gain that you got in there and demonstrate that this is what you get. All right, there is another, obviously, if you want to put this one into the design procedure, that was a question that we have yesterday, right? How are we going to do that, right? We don't have that actually included in the design procedures per se, all right? Except that we have to do all these, graphs and tables and figures that we got. Well, obviously the modulus will be the key parameter for us to be able, okay, what kind of equivalent modulus, right? We're going to have this material offering to that thing, and we can just have some more continuum analysis. There are some stuff that is being done on this one, and it has to be with the wide width tension test, and there are some people that have done that one, in order to figure out the modulus of rupture of that. These are, kind of woven geotextile, and this one is a biaxial geogrid that they have done that. I think this is being Jorge Somber doing some work on that in his laboratory on the UT Austin, and is, his goal is trying to put a modulus in that. So once we got a modulus, then we can just use our theories of material to just figure that out, some inclusion into the design guide procedures. The geogrids surveyability properties requirement for subgrade stabilization are given in here, and I just brought this one because I've been talking several times about this for different classes. So this one is the geogrid class 1, 2, 3, and these are the multi-rep tensile strength, junction strength, ultraviolet. Again, these are ASTM standard that the manufacturer has to use in order to figure out those numbers, okay? And when you get the products from there or from the several companies they're going to be dealing with, or making your licitation on your proposal, then they need to provide some of the stuff, and you need to figure out what kind of class you're going to need to be used on your design. All right, again, the other one, again, is the road base stability. Is when you just get some stiffening, right? A stiffening situation, and again, that works into I'm so happy playing with this thing. So, playing with this subgrade support, again, the load distribution is the key stuff in here for the geosynthetics, right? You want the geosynthetic reinforcement to distribute your load a little bit more even when you put that one. And you can put this one for the stabilization on the load distribution, whether between the base and the subbase material, or within even the base material, right in the middle. There are different reinforcement mechanisms provided by geosynthetics. I just bring up some of these graphs from the Holtz to 1999. And the ones is the membrane kind of a tension support, and that's when the tensile strength is being one of these parameters that you always hear in the geotextile world, okay? So basically, what the theory or what is being claimed is that if you create a tension in this one, is going to be creating, right, a tensile support of the material that you got in there, right? And so this one is the geotextile for that, and then basically this one is a mechanism for that, the membrane tension in the geosynthetic, okay? Bearing capacity increase, I think I talked enough for this one. There is a hypothetical shear surface with the geosynthetic, and some of them without the geosynthetic. And basically, again, there are some studies that have done a very good job on just analyzing, the real values for that. But again, most of the time, 90% of the people use the end values that were found by somebody else, okay? And lateral restraint also, well, this is what I'm talking about, in lateral strain, when you have this tension, then you're going to have a force that's going to be just trying to get, it was tension before, so it's going to try to come back to the place, and that's going to help a lot for the lateral restraint of that material that you have. Base reinforcements, talk a little bit about stress distribution, but they can be placed again within the base of the material or below, between the base and the subbase material, or at the bottom of the base, okay? Functions, the reduction of the permanent deformations in the base and subgrade. I've been talking about rotting and permanent deformation is kind of used the same, all right? In the base and the subgrade are very important, very important. What you see at the top of your pavement, when you see your wheels path, right, the wheel path, you're going to see those rottings, right, those ruts going on in there. Well, this one is obviously accumulation of the asphalt rot plus the granular base material rot plus the subgrade material rot, okay? And when we do permanent deformation calculations, the total permanent deformation, actually, we have done a very good job on the pavement groups to calculate what is the rotting, okay? And it's a parenthesis that I'm doing here because I think it's important for us geotech. They have done a very good work on, okay, asphalt, in asphalt pavements, right? They do to the lab, it's easy for them, and they have it a very well determined, this kind of asphalt is going to have this kind of rot, okay? For the granular material, well, they say it's a material that is elastic. Usually, it's a granular material. Usually what you do have in here are more elastic, right? More elastic is more deformations, and therefore permanent deformations are not a big deal, right? Not a big deal. So they put a small percentage, right? That is going to be through elastic theories on the granular base material. But for the subgrade is when we get all these elastoplastic deformations, right? So what they do is they measure the total deformation or the total permanent deformations at the top of the subgrade. They calculate the asphalt rotting easily. They put a percentage for the granular base material, and whatever is left is what they assign to the granular material, to the subgrade material. Do you see what I mean? So they don't measure it, and we don't. So the only way to demonstrate that all these measurements that they do at the top, which is a reflection of 3 or 4 layers below, right? The only way to demonstrate that if this thing is right is just either doing trenches or doing any other mechanisms of trying to figure out what is the routing, okay, that we get into the field. Okay, so we're talking some of the procedures that are doing that, and it's a difficult thing that will year after year in every conference we see that this is a main problem. We don't have a way of measuring subgrade routing properly, right? Or predicting that, because what we do have is a total permanent deformation reflection on that. So it was a little bit on this one, but it's a big problem that we face as the geotechnical. So everything else is granular basement subgrade deformation. So another function again, keep talking about the base reinforcements. It's going to be the reduction of the permanent deformations in the base and the subgrade layers, and also the reduction of the dynamic deflection and the asphalt fatigue. So talking about the resilient part of it. Benefits: increase the pavement life, saving aggregate materials, they mitigate the effect of the expansive subgrades, and allow for more open graded aggregate, thus providing the potential to drain into sub-edge drains that you may have. So how we determine, and this one is almost to conclude this thing, how we determine the benefit, right, in design procedures. Like I said, there are no design procedures that are running parallel to the inclusion of geosynthetics into the procedure, okay? We have a lot of work to do on this thing. And one of the things that they do is what they call traffic benefit ratio, TBR. And the other one is the base cost reduction benefit, all right? So the objectives of those, kind of design definitions are either decreasing the base thickness, right? Decreasing the base thickness for a given design life, or increasing the design life for a given base thickness. So that's there are the two mechanisms that you do, see? Okay, so you said, okay, I can help at the beginning of my design, on my pavement, right? And I'm going to put a reduction on my aggregate base, right? That's going to be my prediction. And then my road is going to last the 30 years life. Or I'm going to leave whatever I, design without the geosynthetic. I put the geosynthetic. I'm just going to bet that my road is going to last 10 more years, right? So that's the way that we can include this kind of stuff on the design. So the first one is the TBR, the traffic benefit ratio, and it's basically a ratio between the design lives, okay, how much it's going to last. Usually a road is 20, 30 years design, depending on that, okay. The design life for reinforced and then reinforced pavements for a given base thickness. So you got the same base thickness, and you said, okay, my TBR is the number of repetitions, right? This is how you count for the life, right? This 10 years or 20 years is going to be this number of repetitions for the reinforced or the unreinforced roads, okay? And basically, remember the Ashton 93 design equation. We have the equivalent 18,000 wheel repetitions. The reinforced is going to be the TBR multiplied by the unreinforced, okay? So you put this one at the beginning of your design equation, right? Here we go. Right here, right? You just modify this guy, okay? So that's one way of putting on the design, at least on the Ashton 93. And again, Ashton 93 is a very well recognized and used even today method. So we can do that. And the second one is the BCR, the base cost reduction method. Basically, it's the ratio between the base thickness in the reinforced and the unreinforced pavement, right? And I already showed you a little example of how you can save 5 to 6 inches right there, right? And therefore, this one is going to be on the thickness of your granular base material, right? So you go to the structural number of that equation, and you just multiply the thickness of their material, you divide it by the BCR, okay? In that case, you account for a reduction in the granular base thickness, right? So those are the two ways that they have been proposed to do that, and that's how we do the calculations, right? So now the new design guide, and we've been talking also in here for a while, requires, the incremental changes of rotting, of thermal cracking, or temperature cracking, or longitudinal, the roughness thickness with time, right? So in order to put this in here, the key again will be a modulus kind of related material, right? How much modulus, a composite modulus, or something you're going to be increasing the stuff in order to, for the rotting or cracking to be reached at a later time. All right, and last but not least, obviously the payments on expansive soils and how the geosynthetics, it just basically is the prevention of the development of those longitudinal cracks that you're going to be hopefully looking at right now when you go to black soil land in here or any other place on expansive soil. But basically, the geosynthetic reinforcement objective is to prevent the development of those cracks on the pavement. Okay. And for that, usually we just put the geofabric in here, and it usually has to have a drainage objective, okay? A drainage objective. You don't want the water to get into your subgrade material, right? You don't want this big change in suction values. So that's where you put it. You put it in between the subgrade and the subgrade material, which is your problematic soil right here, okay? The type of geotextile products include, we can put non-woven geotextiles in there for separation, filtration, for free drainage, based on the or sub-based materials. Geocomposite, horizontal drainage layer to replace the or augment the free draining base, or woven geotextiles with enhanced lateral draining capacity. This is the kind of a new wave and the fashion right now. Everybody's trying to put all these, composite geotextiles when they have the woven geotextile attached to all these wicking geotextiles that get the water out, okay? In that case, again, the idea is for you to enhance the lateral drainage, okay? To enhance the lateral drainage of, any upward moisture migrating from the high water table, or enhance the lateral drainage of any moisture that coming from irrigation or rainfall, right, from above. Also, control of the pavement damage induced by frost heave. This is that is being also used very widely these days. And again, you just want to cut that capillary rise. Remember, one of the main parameters that you need for frost problems you have is the availability of water, right? Do you remember that one, right? So this one is one that you need to avoid, and one of these one, when you have some wicking geotextiles and you can get the water out, actually you can just avoid that, the frost penetration just continue, because you are eliminating the amount of water that they have available to bring into those ice lenses and the frost in front, okay? And we're also using a lot of in the control of the pavement damage induced by the expansive subgrade materials. And again, in the subgrade materials, what you're trying to avoid on expansive soil is the differential settlement, right? So that's what you're trying to do. You're trying to get the water out so we don't have water ingress through the sides or something that is going to be flopping, and avoiding again those cracks that it formed in this one. So it basically facilitates a more uniform distribution of the moisture content, okay? Again, the problem with the expansive soils is not the water, okay? It's the uneven amount of water, okay? Or the big changes between one point to another point in time. These are the conventional geotextile fibers that can use, and these are the wicking fibers that they're using right now, or they've been engineering to increase the specific surface area, right? There's more surface area, so they're going to be able to get more water into. On this one is basically provide in plain drainage after saturation of the soil geotextile interface. When you have a non-woven geotextiles, it's going to be through large voids, space in its open structure. When you have a woven geotextile, it's through voids, spaces of crossover yarns that you have in there. And the enhanced lateral drainage, which is, this one is the conventional, this one is the weakened drain. We actually are doing some large direct shear 18 inches machining here, and we're testing that guy on expansive soils. Again, I don't give it a lot benefit when I think the expansive soil can just, get a lot of suction in there. If you have a little bit of lower water, it's not going to be easy to get. But there is some benefit when you have a little bit more saturated value, and we're working on that right now, actually. So that involves providing additional in-plane drainage capacity that is mobilized through the suction gradients or weakening within the geotextile yarns. So we're still testing that. There's a lot of work done by Bharat and the Michigan University for those that are interested as well. So it's cool. And this one is a nice image that we got. This is to avoid frost heave. So this is in Alaska. It's a cold land, and basically, there is a groundwater table very close on that. That is the source of the source of water for these very cold soils to start getting freeze. And when they put the geotextile, you can see the color change on these guys, right? You can see that they really is working and not getting into the granular-based material or soil-based material. So that works, okay? It's a dry soil. Enhancing lateral drainage is very important. That's a way to take out away besides all the drainage stuff that we saw last time. So that works. And again, we have a lot of stuff to do is in, trying to incorporate this one into design procedures. All right, so as a summary, there is significant opportunities to improve pavement performance using geotextiles for mitigation of reflecting cracking, for separation, okay, the stabilization of road subgrades, the stabilization of road bases, and improving the drainage. Okay, so you got 5 functions right there. Overall, the geosynthetics have been demonstrated to improve the performance of pavements. So until now, there's sometimes get some more speculation. There is a new product that comes. This is the best product in the world. Sometimes we check it, it's not. But in general, it's being demonstrated that it's going to be an improvement if you use the geotextiles. The state of the practice is rapidly improving, okay, as new research is identifying the properties governing the effect of the geosynthetics in multiple, system or multiple pavement applications. All right, with that I conclude, and I hope you got a lot of questions. You understand the mechanism, the different functions that you're going to have, All right, any questions online? All right, what time it is? 12:30. We finish on time.
Hello, ma'am.
Yes.
Ma'am, here.
Hi.
You were talking about geosynthetic modulus.
Yes.
Yeah. So
Moduli.
yeah. So you are incorporating that into analysis, or it's still in the beginning stage or something?
It hasn't been incorporated. It hasn't been incorporated, and that's what I believe that a lot of people is using that, trying to figure out how tensile strength and how, all this testing that they're doing, trying to figure out, a modulus for that. It's not an easy thing to do, because actually it's an elastic modulus that they're looking for. All right. So yes, I guess resilient modulus is kind of an elastic modulus for the subgrade material, right? Because it's the recovery stuff in there. How to use it, I'm not sure, but I guess if we are able to incorporate, okay, on design procedures, a sublayer, right, a sublayer affected, and this is what I think it can be done, and I think hopefully what we've been doing is that what has been talking a lot about is that, for example, you have, let's say, the granular based material, right? And then you're just going to put a geosynthetic in here, right? A geosynthetic here. We know for sure that for all these laboratory testing that are being done by Jorge Somberg in UT Austin, is that creates area in which the strength increases, right? Because it's going to be confining those granular material to a smaller place, okay? If we are able to figure out, and I think they talk about 4 inches, right? If they know that 4 inches of that granular based material dramatically increase the resilient modulus, right? The modulus increase, okay? Now you can make the design procedure by putting a module, dividing this one into a couple of sublayers and put the resilient modulus in here without any benefit, and increasing the resilient modulus in here due to the inclusion of that. So I think this is what they are trying to do, right, with this resilient modulus, which makes sense because basically what you do have is a zone of influence of the resilient modulus, right, a zone of influence. And if you can give it a number and a thickness in there, right, then we do see the benefit on the design. So I think this is the way this is going. Any other questions? Yes.
Can we use geosynthetic material for improvement of bearing capacity during building construction? Building or any multi-story building. We do lots of expenditure for piling work, pipe cap and these things. So can we use geosynthetic material?
Well, I believe so. I believe so. I haven't checked that out, but I believe so. I don't recall any literature that I have read on that. Have you? Have you seen anything? No. I will just say that to me it is true that the bearing capacity improves, right? Not only that, when you check for bearing capacity, you check local shear failure and everything. You just when you check that those values have increased, I think it can be used for that. Now, applications should be only on shallow foundations, right? Because if you start making holes to do some piling or something down, I don't think it's gonna. I think you bring the benefit of the geosynthetics down, but I'm not. So I think it can be done. I'm very sure there's we can look for some literature on that. It is the same theory. The same theory.
Ma'am, second question. Which material we can use for slope protection, slope erosion?
I think you guys have more knowledge in here. Everybody wants to talk about that? Any material? Well, I understand there are some erosion control, non-woven geotextiles that are used for that. And you see that one, they look like, I'm very sure you guys have some geonatural stuff in here, and I just want to hear from you guys working on that. But I've seen on the geosynthetic side, right, synthetic side, all of these actually is green and everything, right? They make the color green and everything. And you can see there is a bunch of fibers going on in here with big holes, very permeable. Some holes, big holes, small holes that they put on the slope. And basically what they do is they protected it from, getting some water in there. It's not hydrophilic. Well, it's hydrophilic, but it still gets some pores when you can get water in there. But the pores on this one is used basically for the vegetation to grow. Okay, so they make those guys hydrophilic. The water gets, get out and trying to get out of it, run off, but also makes a way that this thing will allow the vegetation to grow and to just get them in place. So this one I saw in the last Geo Congress that I attended, I think it was Geo Congress in March or something, yeah, March or June, that they're promoting a lot of erosion control with that kind of stuff, okay? But I know that you guys here have some geonatural geode stuff going on. You want to talk about it?
Actually, in that case, sustainability is a factor, or otherwise here there is a lot of erosion control mats that's been widely used. Regarding us, we are working on sustainable barriers also capillary barrier systems also. So, and along with bioengineering interventions, and also geonaturals, super hydrophobic mats. So all these kind of things we are working on. So all these can be used, but depending upon what condition, site condition and slope angles, all these things affects.
Right. So they are in use, but you know the thing is the academic world we go very slow, right? We go always very slow compared with the industry, right? They have an idea and the next day they're selling it, right? They're selling it. It doesn't matter how good or bad it is. In Arizona State also, I was making the comment to your professor Bharat. We do have one of my colleagues is working on fungi, mycelium fungi or something, and he's making some sheets that are, you know, great for, you know, control, right? They put it in there and they're very strong. They're testing the tensile strength and everything, and they're made out of fungi, right? So they grow up these things. They're very beautiful fungi growing up in here, and they put some fabric so that thing is gonna get, you know, it's amazing. It's amazing that the stuff that, you know, we can do on the bio side. The thing is we need to get this thing out before these guys start selling all over the place, you know, stuff, right? You know, so I think these are great ideas. We got the materials available, widely available in these climates and, you know, in our countries, and why not, you know, just trying to get it out as much as you can. But again, you know, we need to test this one. These are very good at taking them out. But there are some non-woven geotextile that I've seen that work that way on a slope. And again, anything that stops the water from getting in, right, will do it, right? We'll do it. And some of them just put it on top of it. I've seen that. Some of them just, you know. What I'm trying to do right now is but it's mostly on the benefit. This is the asphalt, the granular base material, and we put a geogrid in here. And okay, this is the geogrid that is so great. What is the benefit of putting these guys, or several layers if you want, into the slope stability analysis for that? Okay, we don't have that. Okay, so what we're trying to do is to figure out, again, how this geogrid is affecting what is the zone of effect of that, and trying to figure out if we just put an extra sublayer in there, right? An extra sublayer in there with certain shear strength characteristics that we can modify programs that are ready for use, you know, on that one. So that kind of stuff is something that we need to start checking around, or check around. And this one has to do with the resilient modulus, but not for resilient modulus, but for a static equilibrium analysis. Okay, there's great stuff in there that you guys can do here in the university, and I'm very sure, you know, you have the theory behind that to just, you know, work great research. And I'm very impressed, very impressed. Yes? I can hear you. Thank you so much.
Do you have any empirical evidence?
Use the mic for the online people too, please.
Do you have any empirical equations to determine the pull-out capacity of the geogrids in the slope regions?
Pull-out capacity, this is actually a manufacturing value. They have to provide it with that, the pull-out test.
But however, when we are incorporating within the soil media.
Oh yeah. So yeah, when you have that one in here, this is the only way that we've been doing that. And actually, with the geosynthetics, we've been doing that before, right? We just on the slope stability analysis, what we do is just to create, a tensile strength right there, and just do the stability analysis with those tensile strength values, all right? But again, what is the benefit? What is the thickness, right? Because if you start getting into very thin pavements, thin layers, or no, just it works. It works like you got and sliding here. It works like you do a stability normally, right? You do that guy, right? That's it.
This question is how to evaluate the pull-out resistance if you don't have any field equipment to do that.
Oh no, well, there is laboratory equipment to do that.
Large direct shear boxes sometimes we use.
Well,
We need to use
okay.
pull-out resistance, but do you have any empirical equations? That's what I was asking.
Empirical equations to do that. For different geotextiles? No, but I'm very sure you can see tables and graphs from manufacturers that they give you the tensile strength, measuring they cannot sell the stuff without tensile strength.
Tensile strength of individual fibers is fine.
Oh, just the empirical equation to estimate it.
If you have some subgrade material which is of having some NC or something, then how do you evaluate that the pull-out resistance is pull-out resistance on the fibers?
The pull-out resistance, well, pull-out resistance is the material, or you mean the with the soil?
Yeah.
No. Well, the only thing, but we don't measure it. When we do the large direct shear, you just basically hold, right? Hold in place the geotextile, but that doesn't measure the pull-out resistance, right? The only way I've seen measuring pull-out resistance is in the material by itself, right? And they just put it on this thing and then just, find out the way to do that.
Actually, when the slope is trying to fade,
Mm-hmm.
that is the resistance that is coming from the geogrid between the layers, right? So that is required to do the analysis. So
Right.
it is actually required.
It-
Under the wet conditions it behaves differently, under the dry conditions of the soil it behaves differently, because the adhesion between the soil layers and the geogrid,
Mhm.
that varies.
Okay. Yeah, it could be different for different, conditions. But what I've seen in there are several programs that they do this one, and they just, do the tensile strength right here, right? The strength going out in here. You said that the pull-out resistance is going to be a function of the soil type in which it is, and probably yes, I believe so, but I haven't seen that. Haven't seen the data, like, empirical data that we can check that out. Mm-hmm. But no, I don't have that information, but we can check. Tensile strength, yeah. If you put a force like this in your analysis, right? Everything that you have in here, and you got that force in here, that's how I've seen that happening. Okay. But this is tensile strength of that thing. It's the same thing as you have a nail, right? Exactly. Exactly. So what they do is they use the anchor programs, like, to estimate the stuff, and they just put a tensile strength in there out of every one of the slices, right? But it's just the material thing. It's not something related to the strength in, interaction with the different soil type. But this is a very good idea, different soil types or different moisture contents on the soil, and how this might affect the value, right? Usually what we use is the manufacturing value for the material itself. Yeah. Mm-hmm. Interesting. Great questions, yeah, great questions. Any other questions? All right, guys, so you guys are well studied for the exam this afternoon? I think the question, how many were going to fail today in here? All right, thank you very much for your attention, and I hope you guys enjoyed it, and I'll see you then in the afternoon. Finalize that, what, 2:30? We're going to continue at 12:30, so we got less than 2 hours, yeah. they take an exam as well?
No,
Yeah, okay.
exam is only for the offline participants. All right. So in the morning, Professor Claudia was presenting different geosynthetic materials. Right? Geosynthetics have been used in road, rail, and many other applications, slope stability, and many things. In India and of course elsewhere, there's a lot of effort to make geonaturals, right? So alternative to geosynthetics. So as I think in the first day I think mentioned, geosynthetics could be a kind of a sustainable solution. That's one kind of a approach, or some school of thought thinks that they are actually a sustainable material, not because of the characteristics of the material itself, because it can sustain for a longer period compared to without using geosynthetics, right? So the life of the structure would be improved. So with that it is more sustainable. That's one belief. Another belief is that that is also adding to the the environmental effects, because the microbes, soil microbes, are getting affected by the presence of microplastic and nanoplastic, and that is again coming to food cycle. That is another school of thought, and there's a lot of attention given to the making naturals. So some effort has been made from our group. So one of that is making clay liners using natural material. So as this is not a geoenvironmental, we didn't touch this particular topic perhaps, but we also use something called geosynthetic clay liners for containing the waste in landfills. So their application is a tremendous application, because a large area has to be covered with a GCL. GCL essentially consists of woven and non-woven combination, either stitched, needle punched, or with a bond, chemical bond. So that kind of a thing that I actually generally make. So in between you will have clay called bentonite. Bentonite is highly plastic clay which is mined and which is used, generally sodium bentonite is used, and bentonite is used in granular form. So they appear to be like a fine grained fine sand, around 0.6 mm or so. Average size is about 0.6. So it's not powder, it's a granules. So they are stitched between woven and non-woven, and they make it using needle punching or stitch bonding, right? So these two varieties are commercially available. All manufacturers, they use this. I mean they produce this, and many landfill engineers, they use this. So now the granulated form of bentonites, they break down because they have certain bond. While during making the process itself, you will separate the powder bentonite and granulated bentonite. So this granular form has come here. When the water penetrates through this granulated form of bentonite breaks into number of particles, and larger voids that are present between the particles, between the granules, will be occupied by the particles itself. That is called sealing, self-sealing ability of the bentonite. So with that, the hydraulic conductivity is brought to very, very small, 10 power minus 10, 10 power minus 11 meter per second, very small value. So diffusion is predominant. That is a slow process anyways. So in this, there is some concern that you are using again certain waste. There is actually waste or polyester or whatever, which is coming to the landfill and then which is staying forever. So we have made some effort in making natural ones. So we have non-woven, woven. This is needle punched. In between you have GB, granulated form of bentonite. So same density as the commercial one. So this we have done in Birla Jute Mill as part of one of the research project what we have from NJB. and we achieve better results compared to the even commercial one. Better results because commercial one has certain disadvantages, such as needle punching itself, which causes more hydraulic conductivity than bentonite itself. So from our group, Himanshu, Sahil, all of them started working in this, and Himanshu previously, and after that Sahil started working. So we have evaluated hydraulic characteristics, diffusion with salts, and hydraulic characteristics under several back pressure conditions, etc. So test results are complete, and we are about to apply for a patent. So similarly, we have you have these things. No, you didn't bring. Yeah, he made a super hydrophobic textiles, natural textiles, geotextiles, which could be used in erosion control as erosion control mats. We have geocomposites, which are used for slopes for controlling the erosion. So similar effort that has been made. Similarly, a lot of other things. Mahesh complete work is on that only. So he uses several geonaturals from banana fibers to coir, everything. Right. So I think he also brought some samples. You can show it maybe after some time. Maybe after the distribution or informally you can also interact with him. So there are interesting topics that have been covered. Today she has covered on pavement geotechnics, application of geosynthetics, and evaluation of moduli, and similarly we had discussion on slope stability related things and how the pavement should be flexible, low volume roads. All such discussion has taken place. Amazingly, at least I believe a very good amount of topics have been covered. So this GIAN program, as I mentioned earlier also, which is very, very useful for the participants to interact with the global experts. Otherwise, even if we attend a conference, we hardly get a chance to interact with the experts. But here we stay together for nearly 5 days to 10 days. We chose to have 5 days program now, and where we get an opportunity to interact, and this will translate to a long-term collaborations and networking. So that is the main aim. I'm sure this would happen in coming days. Yeah, and so with that I conclude, and I congratulate everybody for participating, and going to get the participation certificate, as well as you will be getting another certificate, second certificate, for because you have written an exam, you will get a grade sheet. So you will get 1 grade for this 5 days course, which will be useful or acceptable in all different universities, right? Thank you so much. Anything you want to say, a few words or something?
No, well,
closing remarks.
I think you're absolutely right that I think one of the best thing from this interaction was the fact that I was able to talk to you and get a lot of questions on the breaks. Okay, so that really helped a lot to finalize some of the topic that we just studying here, and then all these questions that come after the interaction and after the lectures were very, very finely discussed later on by the students. So I really appreciate to all of you that made questions and that just pointed out something on this. I really appreciate that, and I really learned also a lot from the group that you guys are doing here. That amazing research, and I think this should be an opportunity for you, those courses, just attend as many as you can, because I think it's much better. It's much better just not only looking at the theory, but also just getting the practical side of it. I think it's very important for you to see where all these things that on the textbook goes, right? At the end of the day, what are you going to be doing over there? Is a little part of all of this. You understand the fundamentals in here, and then you get exposed to some of the practical applications on that. So I really appreciate the opportunity to be here. I learned a lot. I really enjoyed being here for the first time in India, actually. So, I have had a lot of interaction with very good friends from India, but being here is a different thing, right? I really enjoy it. And thank you very much for all of you guys that took the time to, to talk to me, take me around, help me navigate the city. So I really appreciate your invitation, Bharat. I think it was absolutely a great experience. And I hope you guys have a lot of questions by email, or we can just discuss. I use Zoom with my students all the time. They know my Zoom is always open, and they just shut up if I'm not on campus. So please do so. I think there's opportunities for more discussions, for more collaborations, not only on the academic side, but also on the consulting people that we have in here in the audience. All right. So I really appreciate it, your attention. I think it was a great group of students. I'm going to be grading this one, so I'm not going to fail anybody. Don't worry about it. So I really enjoyed that, and I congratulate you for completing the course. Oh, that's a good idea. Feels like a sand in here.
I think it came out because
Came out,
there's
yeah.
an opening here.
But that's a bentonite, right?
Yeah, better.
Oh my goodness.
Over 0.6 mm size. Yeah. So I'll call the names one by one, and please come here and receive the certificate. Okay? Himanshu first. Sorry. We'll give it here and we'll give.
All right.
So you can also give.
Congratulations. It should be in the middle.
Oh.
You're this time now.
Damodar?
Congratulations.
Mrunmay? Mrunmay Adhikari? He's a BTech chap. Bachelor's.
Yeah, I know. Congratulations.
You know, he's a concept. Pushkar?
Congratulations.
Dhanesh? Dr. Dhanesh?
Congratulations.
Famous music director from Tamil Nadu.
Ah.
She has the same name.
There we go. Congratulations.
He's a professor from a well-recognized institute, college from Tamil Nadu, southern part of India.
Congratulations.
Abhishek? Pawan is Marathi, right? No? Huh? Annapurna? Next. Jitendra Kumar. He's from Bangalore. He's from Bangalore.
Congratulations.
Pradeep. Sanjay next. Pradeep, Sanjay.
Congratulations.
Thank you.
Congratulations.
Thank you.
Congrats. Sanjay.
Sanjay. Congratulations.
Thank you.
Congratulations. Rajkumar. Full चला गया ना?
Yes.
Congratulations.
You are actually covering her.
No, I
This
could-
one,
I could see.
Abhishek Kumar Pal.
Congratulations.
Basil. Vishnu.
Congratulations.
Congrats.
I'm wearing things.
Look at that. Next, Bharat.
Congratulations.
Congrats, Kuldeep. Bharat. Kanan. Congrats, Kanan. Mahesh.
Mahesh. Congratulations.
Achintya.
Congratulations.
Okay.
Thank you.
Trishan.
No name repeated. Congratulations.
Pooja. Sajid.
Congratulations. Thank you.
Sajid.
Congratulations.
Good.
How did you know that? Congratulations.
Ganesh. Vinit. File is from industry. Sorry. Sorry. Shenzhen. Shenzhen. Amit Singh. Dr. Amit Singh.
Congratulations.
Bonami.
Congratulations. All right.
Two online participants, Imad and Edwin. So you will receive soft copy participant certificates. Okay. Thank you, Imad.
Thank you, sir. Yes, sir. Thank you. Thank you.
So we are done now.
Oh, yeah?
Yeah.
And I'll get an email to you, Emad. I already got the notification that you need some data. No, that's it.
Okay. So we have a high tea arranged. Okay.
All right.
So with a couple of sweets and other things.
Wonderful.
So yeah.
That concludes the course then.
Yep.
Yeah.
Yep.
We apply for all of you. Good.
Yeah. Thank you.
Yes, this one is good.
This is green turn. Yeah. We'll have subject. We'll have a photo together. Yeah.
You guys behind.
Yeah.
All guys go back.
Including you.
No, right? We have got directly used.
All guys behind, yeah. All right.
You can go from.
Oh my God.
So sorry.
Photo.
You're special.
All righty. Get closer. You're going to get into one of those chairs. Oh my goodness. It has wheels on it. Sorry, you mean cheese? Thank you.
Thank you.
Oh, nice.
Thank you so much. Thank you very much.
Oh.
Mahesh for all the help. Mahesh and all my other students.
Sahil,
Sahil, Vishnu.